In this podcast, we're going to take a look at the basics of computer architecture. Every computer architecture that I can think of starts with memory. Memory is a collection of cells that have both contents and they have an address. Think of it as a house. You've got stuff in the house, and the house has an address. Now, not surprisingly, in computers, all of this stuff is done with ones and zeros, as we've seen before. The contents of the memory are stored in binary, and the address is also found in the computer in binary form. In this particular picture here, we can see that we have 8 bits worth of address, or 2 to the 8th possible memory cells, 256 cells. Each cell can store 8 bits, or 1 byte, of data. There is absolutely nothing magic about the memory in a computer. In fact, here's a simple one designed using Logisim and using the 4-bit memories that we built in our last lab. I'm not going to go into the gory details of this, but you can see the data flows from the 4 data inputs, D0 through D3, in the pink lines into each memory cell. The address lines, 2 of them, giving us 2 to the second, or 4 possible blocks of memory, flow in the green lines, and you can see they're all connected to AND gates. What those AND gates are doing is ensuring that only one of those memory cells is selected at any given time, the one whose address is on the address lines. And all of those memory cells are then ORed together to produce the output of the current active memory cell. Notice that it's basically one circuit stamped out a whole bunch of times and then tied together. There's nothing magic about memory. It's just logic gates. Lots and lots and lots of them. Speaking in lots and lots and lots of gates, this is a current 512-bit memory, megabit memory, that you can buy today. And you'll notice it doesn't look a lot different from that circuit that we saw before. I've circled the clock line way over on the right. There's a right enable pin on the left. You'll see addresses down at the bottom that run from BA0 and BA1 and then A0 through A12. And you'll see data lines up on the top that are labeled DQ0 through DQ15. So it has 16 bits worth of data. The addresses are actually divided up into 4 banks. That's the BA lines. And then they use a little trick here. They actually strobe 2 sets of addresses across those address lines based on timing so that they don't actually have to have an entire 18 bits worth of addresses. They use address lines A0 through A12 for 8K worth of addresses. And then a split second later, they read a different address off of A0 through A9 and get another 1K. Multiply those together, and that gives you basically 8 meg. So 8 megabits times, or 8 meg times 16 bits times 4 banks of memory gives you a total of 512 megabits. Now that memory is a particular kind of memory known as RAM, Random Access Memory. You can write and read every location on it. The only problem with it is that you lose everything when the power goes off. In fact, in this very, very popular kind of RAM, known as DRAM or dynamic RAM, it loses its memory cells very, very rapidly, and so it actually has to periodically refresh or rewrite what's out in memory. Now, SRAM or static RAM doesn't have that problem, but it is much more expensive. When you absolutely don't want to lose what's in memory, you put it in what's known as a ROM, a read-only memory. These are manufactured to be permanent and cannot be changed. These are found in many embedded devices like your microwave oven, for example. You're probably just as familiar with flash memory. Flash memory is really closer to ROM than it is to RAM. It's actually the latest version of what's historically been called programmable ROM. And that basically means it's mostly for reading, but you can write it if you work hard enough. In this current version of flash memory, you can generally erase big blocks of it at a time, but it takes a little while, and you can write individual bits. It also wears out. Current technology wears out somewhere between 100,000 and 1 million cycles. Now, if you're just recording MP3 files for your iPod, that's not a big deal. If you're trying to use it to compute heavy-duty stuff and play graphics games in a computer, you're going to run through those 1 million cycles very, very rapidly. And of course, flash is a lot slower than RAM memory. The key insight that turned memory into computers was the idea that memory could be used not just to store data, like your MP3 files, but it can also store instructions that describe how to process the data. Now, this insight was not a flash for one individual, but it evolved over a period of years from a whole bunch of people who worked sometimes apart and sometimes together. Eventually, the idea came known as the stored program computer, and the program is another word for the instructions that are used to process the data. And the most common architecture using this stored program concept has come to be known as the von Neumann architecture, and it represents probably 99% of the computers in use today. As you see, memory is separated out and contains both data and instructions, and a central processing unit is a separate piece of logic that is used to process the data based on the instructions in the memory. Now, a computer isn't terribly useful unless it has some way to get some input from the outside world. Input devices tend to put their data directly into memory under control of the central processing unit. So the interaction might go something like this from your keyboard. The keyboard says, "Yo, CPU, got some data for you." The CPU would say, "Okay, go stick it in memory location 14, will you? Let me know when you're done." "Got it," says the keyboard. Similarly, computers that listen but never say anything aren't terribly useful, so we also have to hang some output devices that again operate under the control of the central processing unit but can interact directly with memory to take data from memory and display it to the outside world. Now, you're also probably aware of things like disk drives that you can use to store information when it gets too big, basically, for memory. We'll talk about those in a lot more detail when we talk about file systems later on. Now, all of these components in the von Neumann architecture are connected with something we call a bus, a computer bus, a data bus. And different buses are used for different things. In many cases today, the bus that connects the CPU and the memory is a different bus than the one that connects the input and output devices. For example, you'll see down there at the far left, PCI slots are used to connect things that need very fast access to memory. An ATA bus is often done with a data cable to connect things like disk drives. And then, of course, you're all familiar with the universal serial bus, which is used to connect even slower devices. Now, taking just one finer-grained look inside the von Neumann architecture, the CPU itself is broken up into 3 pieces. The first of those pieces we'll talk about is the arithmetic logic unit. It's basically the place where all of that binary addition and negation, multiplication, and floating point operations and stuff go on. It does Boolean operations, and it operates on data from the memory, retrieved via a bus, and also in things called registers. Registers are essentially very high-speed, special-purpose memory that are right next to the CPU. They're not cache, that's something different. We won't really get into that level of detail. There's only a very few of them. There's 16 total in the latest big Intel processors. They are connected directly to that arithmetic logic unit. And one of those registers is the first among all of them. It's known as the accumulator, and it's the place where almost all of the ALU operations operate. We won't have a lot to say about the details of the control unit, but it is the organizing force in the computer. It controls what goes on and in what order. It uses 2 very special registers, however, that are extremely important. The first of those is called the instruction register. When the CPU pulls an instruction from memory, it has to have a place to put it, and it puts it in the instruction register. It also has to know where the next instruction is in memory, so it can go find that one after it's done with the current one. And that address of memory is stored in what we call the program counter. So to process an instruction, what the CPU has to do is fetch the instruction from memory. Once it's got it from memory, it brings it into the instruction register, where it decodes it to figure out what to do. Now, instructions may include what we call operands. They're the things that the instruction wants to work on. An add, for example, has to reference at least one or two numbers that need to be added. It can get these operands either from yet another memory location, going off to fetch the data this time instead of fetching the memory, or it actually might be information that's right in the instruction itself. Finally, when it's got all of that figured out, it actually has to call then on the ALU to do the appropriate operation, to execute it, we say. Not kill it, just make it happen. Now we're going to explore these concepts more in something we call the super simple CPU. That's in the next podcast for a quick demonstration of it, and it's also the essence of our first lab in this unit.